to split this section into 2 days of notes, so we're actually going to do just the first part of these today. I don't think it's like a super difficult section, but kind of all together it might just be too much for one day. So I think it's going to be like super easy on both days, but I think all together it just would have been too much. So we are going to talk about similarity in right triangles today. So yesterday we talked about how to prove triangles are similar, and this was just any triangles. Okay, it didn't have to be right triangles, but today specifically we are talking about just right triangles. Okay? So if you have a right triangle, what we are going to do, so this triangle ABC right here is going to be like our original triangle. What we're going to look at today is what would happen if you drew what's going to be called the altitude of the hypotenuse. Okay, altitude is height, okay? And so if I'm talking about the height, remember it has to go straight up to that other vertex. You should see that right angle. But you have to be kind of careful about where you draw it. So this picture is nice to start off with because the triangle is like sitting on its hypotenuse. So when you draw the altitude, that's CD right there. So how tall is the triangle? Right from the hypotenuse straight up to that top vertex, straight up to that right angle. Okay? We're going to have to be kind of careful about drawing that today. Okay? But the altitude of the hypotenuse, okay, the big thing is it has to go from the hypotenuse to the right angle. Now, when that happens, when I draw this altitude, I actually take this big original triangle and I kind of create two smaller triangles. Okay? And they're kind of twisted and turned and flipped a little bit here. But if you take this triangle on the left right here, okay, triangle ADC. You can see it right there. And you kind of, what do we do here? They kind of like flip it up like this. Okay? And you have triangle ADC sitting on its hypotenuse right there. So the hypotenuse is that altitude. Okay? So kind of notice that the hypotenuse right there, okay, is, okay? Sorry, it's not the altitude, it's that outside edge right there. Okay, the hypotenuse, all right? And then the other triangle, okay, the triangle, maybe we call it CDB. Okay, now so if you look at it here, the hypotenuse CB, okay, it's the one that it's sitting on right down here, okay, but you can see that triangle CBD, okay? So I have the original triangle, and then I have these two other separate triangles. Theorem 7.3 tells me that all three of these triangles are similar. Okay? So, from going from the original triangle, which is triangle, maybe we call it ABC, that original triangle is going to be similar to, now what's nice, and this is what we're going to have to practice today, is whenever you take it from that original triangle and then copy it down, okay, getting the order of the letters correct, okay? So angle A, okay, for this one is going to be triangle ACD. If you go in that same order there, which is also going to be similar to triangle. Now this time it would be CBD. Those three triangles are similar. So what we're going to do today is just practice taking that big triangle, splitting it off into those two triangles, and then writing this similarity statement. The other thing we're going to work on today, which seems a little unrelated to that, but then on Monday we're going to tie like these two things together. The other thing we're going to talk about today is what is called the geometric mean. The geometric mean. Now, your previous experience in math, you found the mean, and in math, mean has nothing to do with the math teacher. So they're all really nice. But, okay, so, no, the mean in math, typically, what's another word for mean? Average, right? So if you had two numbers and you wanted to find the mean or the average, you would add them and divide by 2. If you had 3 numbers, you add them and divide by 3. What we're going to talk about today, it's kind of similar, but it's called the geometric mean. So the geometric mean, okay, we're looking for x. My geometric mean is the x in this case right here. But to find the geometric mean, if you're looking for the geometric mean between a and b, okay, 2 numbers, a and b, whatever they are, you could set up this proportion where a over x equals x over b. So you've got something over x and then x over something, okay? Those 2 numbers that are called the extremes, okay, the extremes, what you would do is you would have numbers where a and b are, but you're looking for x. So although we don't know what a and b are, it's a proportion. We solve a proportion using cross products, so it's not numbers, it's variables. We can still kind of go through this. So if I were to do cross products, I would take a times b, which would just give me ab. And then the other cross product would be x times x, which is x squared. Now, to find the geometric mean, I would need to find x. Not x squared, but how do we get rid of the square? Okay, use the square root it. Okay, so x equals the square root of AB. X is how you find the geometric mean. To find the geometric mean, whatever the 2 numbers are, you multiply them together and then take the square root. Which, the mean, the regular mean, the average, if you have 2 numbers, you would add them, divide by 2. If you have 3 numbers, you would add them, divide by 3. For the geometric mean, if you have 2 numbers, you multiply them and find the square root. If you have 3 numbers, you would multiply all 3 of them, and guess what we do after that? The cube root. We find the cube root. It's kind of related, okay? So, if you wanted to, you could set up this proportion every single time, but guys, find the geometric mean, multiply the numbers, and then take the square root, cube root, fourth, how many numbers you're talking about. For this class, we're just going to do the geometric mean of 2 numbers. So to find the geometric mean of 6 and 15, you are going to take 6 times 15, which gives me 90, and then you would take the square root of that. Now, the square root of 90 is not a perfect square, so what we want to do today is we want to write this in simplest radical form, which means you either need to cake 90, if that was the method that you liked, or most of these numbers today, guys, are going to be simple enough that you can do the perfect square factor method. So remember, the perfect square factor method is looking for numbers that go into 90 that you can take the square root of. So I can take the square root of 4, and of 9, and of 16, and 25, and 36, and 49, and so on. So out of those numbers, what one of those numbers goes into 90? 9. I can take the square root of 9. Those are the numbers we're looking for. So it'd be 9 times 10. You're going to break it down into that product of a perfect square factor. Now, even though I broke it down into 9 times 10, it's still underneath the radical. So I have the square root of 9 times 10. I can take the square root of 9. That's why we found the 9. The square root of 9 is 3, but I can't take the square root of 10. So it stays the square root of 10. So your simplified answer, the geometric mean, would be 3 square roots of 10. Okay, let's get this glued into page 75. We will finish out the rest of the notes on Monday. This is section 7.4, Similarity in right triangles. All right, so the first thing we're going to do is kind of what we did in the first example when I was explaining that theorem. So we're going to have the diagram, okay, of a right triangle, and we are going to write a similarity statement that relates to 3 triangles, so the original one and then the 2 that are created by drawing the altitude. So we're going to draw a beautiful right triangle. And my beautiful right triangle is going to be triangle XYZ, excuse me. Now the other one was drawn nicely, so whenever I could draw the altitude of the hypotenuse, it was just how tall is the triangle. But that's not the case here. The height of the triangle as it is right now is not the altitude of the hypotenuse. The altitude of the hypotenuse is where you go from the hypotenuse straight to the right angle. Okay? So it's not going to go from the middle of the hypotenuse. It's going to take the shortest distance from the hypotenuse to the right angle. So it's more than likely going to be off center a little bit. And we're going to call that W. And then we know if it's the shortest distance, it should be a perpendicular line. So this is the information they're going to start by giving you. Okay? What we want to do is we want to write the similarity statement that just says the original big triangle is similar to this triangle, which is similar to this triangle. Now, in my mind, it's kind of hard to see because they're all kind of all in one. It would help if I just had the 3 separate triangles. It would be super easy to write the similarity statements, especially if they were all like oriented the same way, and then I could just do the order of the letters. So that's what we're going to do. We're going to copy down the 3 separate triangles. So the first triangle should be easy. I mean, it's just that triangle X, Y, Z. Exactly as you see it. X, Y, Z. Now, my other triangle, okay, the next one, it's going to be this one over here on the left. Okay, so this one right here. So, it's going to make it easier when you write your similarity statement if you draw it so it looks like this. So, it's going to be smaller, but it still should have, okay, that right angle. Okay, so the easiest vertex to label would be the right angle. What point is my vertex? W. Okay. Now I think just kind of the next thing, I mean, you know that your hypotenuse is ZY. The picture on your homework is going to hopefully be easier to maybe see. But the shorter side, which I didn't do a great job of labeling here, okay, it's going to go W to Y and then to Z like that. And then we'll go ahead and go to the other one. Okay, so once again, I think it's going to help if we kind of make it look the same. It's similar, so it's the same shape, just not the same size. Once again, the easiest vertex to label is probably the right angle. What's my right angle? It's also W. I didn't write the right angle there, but we could. Right, this one is also W. Okay. Now, if I go from the right angle to, and like I said, the picture in the book is going to be easier, but I mean, you can tell kind of the smaller angle. Right, is going to be Y and then X. Okay, so this is the hard part of this, because once you do this, we already know because of that theorem that they are similar. We just need to write the similarity statement. Okay, and the similarity statement, since I already wrote them, so they're all corresponding, nice and picture perfect, we just have to label all the triangle or name all the triangles the same way. So if we start with triangle X, Y, Z. So if I start here, I'm going to go from the top down and to the left. Since I wrote out my triangles this way, we're just going to name them all the same way. So triangle, this one would be Y, W, Z. Y, W, Z. And similar to, we need to do the same thing with the last triangle. X, W, Y. Okay, you'll have a couple of those. Alright. And then the only other thing we're going to practice in your homework today is finding the geometric mean. So remember, if you forget how to find the geometric mean, it's similar to finding normal, I think it's arithmetic mean. Arithmetic mean, you add, divide by 2 or 3, how many ever numbers. For geometric mean, you multiply and then take the square root. So if I wanted to start by finding the geometric mean of 3 and 27. 3 and 27. Instead of adding and dividing, we are going to multiply. 3 times 27 is 81. and take the square root. This one's easy. Square root of 81, 9. So the geometric mean is 9. Now number 3, if I have something that says 4 and 18, 4 and 18. Once again, the geometric mean, you multiply them together, because keep in mind, they're the cross products, okay? You would have 4 over x equals x over 18. If you did the cross products, you would multiply 4 and 18. We'd get 72. But that would be equal to x squared, because you'd also be taking x times x, which is why we take the square root to get rid of the square. Now, like in the one on the left-hand side of your notes, you wouldn't want to leave this as a square root of 72. I don't want you to turn it into a decimal. I want it in simplest radical form. So you can either do the cake method, okay, so cake 72, go on from there, or I think most of the numbers today are going to be easy enough that you can find the perfect square factors. Now, there's actually 2 perfect square factors of 72. You want to find the biggest one. Okay, so I'm going to come back to that one. So 9, you can do 9 times 8, right? Here's the problem with that. 8 also has perfect square factors, so you have to break 8 down as well. You can do that, but keep checking. There's a larger perfect square factor of 72, and it is 36. Right, remember the perfect square factors. These are the numbers that you can take the square root of. So this would be the square root of 36 times 2. The square root of 36 is 6, and I can't take the square root of 2, so it stays the square root of 2.